introduction, and thanks for having me be able to give this talk here. It would be really nice to visit in person one of these days, but it's nice also to visit virtually here. And so today what I want to tell you about is about the structure of jets in gamma ray bursts. I will talk specifically about the gamma ray burst that followed the neutron star merger detected in gravitational waves. This is 17017. But also I will try to talk beyond that burst about what we know from other lines of evidence and so on. So to begin, let's start with a brief introduction to gamma ray bursts so that we're all on the same page. And these gamma ray bursts are very bright, very extreme explosions that occur all across the universe at distances that are typically very large from us. These release huge amounts of energy over very brief periods of time, maybe seconds, fractions of a second, up to hundreds of seconds. And the origin of these bursts can be through two different channels, either the collapse of a massive star into a compact object, either a black hole or a very strongly magnetized, rapidly rotating neutron star, known as a magnetar. This channel will produce what is known as long gamma ray bursts. Those are the ones that last hundreds of seconds. Or there is a separate channel, which is that you have two neutron stars, which are in orbit around each other. Over time, they lose energy in the orbit due to emission of gravitational waves. They merge, as we saw very spectacularly in 17017, and that again produces a compact object that is either a black hole or a very strongly magnetized neutron star that then acts as the so-called central engine and can launch this relativistic jet. So either way, we've formed the central engine. We're launching now a relativistic jet, as you can see here in this cartoon. And due to some kind of interaction that happens within this jet, so this is a jet moving at a speed very, very close to the speed of light, a fraction from the speed of light, we get some kind of internal process that dissipates the energy and creates a radiation that is seen mainly in gamma rays. This is known as the prompt phase of the gamma ray burst. It is characterized by this very variable emission as a function of time, typically in gamma rays, and lasting between a fraction of a second to hundreds of seconds. After this happens, the jet starts interacting with the environment around it, and that produces another electromagnetic counterpart, which is smoother, much longer in time scale, and is seen all across the electromagnetic spectrum, from X-rays and sometimes even very high energy gamma rays, all the way down to radio. And in the lower wavelengths, in the lower frequencies, sorry, it can be seen a very long time after the original burst, months, and in some cases, even years after the original burst. So still, even though we have this very broad brush picture of what gamma ray bursts are, many things remain open and still unknown in this field. And we can go through the chronology of a gamma ray burst, and almost in every step of the way, there is some very big question that is still unanswered. For example, just to give you a taste of this, we talked about this central engine that is launching the relativistic jet. We still don't know, is it always a black hole? Is it actually more often a rapidly rotating magnetar? There are ideas suggesting that either one could play a role, but we still cannot say for sure. Then we have the jet itself, and for the jet itself, again, there are two distinct possibilities. Either the energy content of the jet is dominated by matter, so simply the kinetic energy of the matter that is moving within the jet, or else the energy in the jet is dominated by Poynting flux, so it's actually carried mainly by electromagnetic fields. Then we know that this energy has to be dissipated, and again, there are different ways that you can dissipate this energy, which in part relate back to what is the way in which the energy content is carried through the jet. So this can be shocks between parts of the jet that are moving at slightly different speeds. This can be magnetic reconnection if we have most of the energy in electromagnetic form, or this can be some nuclear reactions and so on. So this is another major step that is uncertain, but in some way this bulk energy is dissipated into energy in particles that can radiate, And then again, depending on how you do that and where you do that, the radiation processes are going to be different, and it's not clear which of them is actually giving the prompt gamma ray signal that we observe in those bursts. So is it synchrotron radiation? So this is created by very relativistic electrons or protons gyrating around strong magnetic fields, or is it photospheric emission, for example? And there are other options as well. So this is maybe a bit discouraging, but a silver lining is that at least for the second part of the GRBs, for the GRB afterglows, we actually understand them pretty well. So at this stage, what is happening is that you have the jet, and it starts to expand into the external environment, and eventually this external environment starts to slow it down. The dynamics that are taking place due to this process of the jet being slowed down, being decelerated by the external medium, are governed by this self-similar solution developed by Blanford and McKee. And then what happens is that you have shocks that are going one forward into the external medium, known as the forward shock, and one backwards into the jet material itself. This is the reverse shock. And these electrons are going to be accelerated mainly in the forward shock. They will be accelerated to relativistic energies. The magnetic fields in this region are also going to be enhanced. And so this will lead to radiation through synchrotron and maybe also through synchrotron self-compton. Or at least you will see some effects from the cooling because of synchrotron self-compton. And this produces broadband emission, and you can predict the flux as a function of frequency and time due to this process. And this matches very well with our observations of GRB afterglows, especially at late times, especially at thousands of seconds and later after the burst. So that part is quite well understood. And I want to give you a bit of an intuitive feeling for how to understand what is going on in this later stage of the GRB afterglow. So we can look at this sort of canonical sketch of a GRB afterglow. And here we should caveat that the different bursts can look quite different from each other. And sometimes they may not have all of these phases that are shown here. For example, phase 2 and phase 5. So this kind of flattish part and this flaring part, these are parts that are seen in some bursts, but not all. But what I want to focus on here is this part 3. So this takes place after about 1,000 or 10,000 seconds since the beginning of the burst. And here what happens is that you get a decline of the flux or the luminosity roughly as t to the minus 1. And I want to convince you that t to the minus 1 is very simple to understand, and the small correction on top of that is not important really for our first approach. And the reason is the following. So imagine that you have a jet with some opening angle theta naught, as you can see here in the picture that I drew on top. And imagine that this material in the jet is moving at a Lorentz factor gamma, such that 1 over gamma is much smaller than theta naught. Then, because of relativistic beaming, you can only effectively see radiation that is coming from at most a latitude of 1 over gamma above the line of sight. And that is just because of the fact that material from a larger angle is going to be very strongly suppressed due to Doppler beaming. And this means that you are seeing effectively this patch of 1 over gamma that is smaller than the size of the jet. And you're not aware that the jet has any edge. So the only quantity that you can be sensitive to at this point is the isotropic equivalent energy of the jet. That is the energy that the jet would have had if it had no edge at all, if it was completely spherical symmetry. And this means that to first approximation, this quantity is conserved, and so the luminosity will go as 1 over t. This continues as long as gamma is decreasing, but still such that 1 over gamma is smaller than theta naught. So you see here, gamma has decreased slightly, so 1 over gamma has increased. This continues more. Eventually, 1 over gamma becomes larger than theta naught, and now suddenly you realize that something is missing. Sometime at this point, you realize that there is some of the emission that you're not receiving because there is no jet there anymore. And this means that the light curve that you will see will now decline faster than it was going so far. And on top of this, there is another effect here, which I kind of have hid from a view in this schematic picture, which is at this point, also the jet starts spreading laterally. And both of these effects cause a faster decline in the slope. But the bottom line is that we have this characteristic point here, where 1 over gamma is of order theta naught, which is where we see the full, not isotropic equivalent, but true energy of the jet. And beyond this so-called jet break, we have this steepening of the slope. So now let's move to talk about 170817. 170817 was the first gamma ray burst detected in coincidence with a neutron-star merger that was seen in gravitational waves for LIGO. So we saw the gravitational wave merger for LIGO, and within seconds, we saw this gamma ray burst as well that followed that. And then later, there was lots of other electromagnetic counterparts due to the kilonova and the gamma ray burst afterglow that followed at later times and at longer wavelengths. And so, of course, the fact that we were able to detect the GRB with the gravitational wave trigger has meant that people were looking at this GRB with all telescopes and as sensitively as possible to try and detect anything that comes from it. And therefore, it's not surprising that we have this wealth of information. But also, the fact that we have this trigger through gravitational waves meant that we were able to see GRBs in the way that we usually cannot, because the trigger through gravitational waves doesn't care about the angle relative to the jet. And that means that if usually jets are very narrow, this allows us to now view these events from an angle that is much greater than the typical viewing angle, and therefore from a distance that is much closer, because there are many more events available to us if we don't need to only select those that are pointing exactly towards us. So indeed, the GRB that followed is by far the faintest short GRB ever seen, about 10,000 times less luminous than any other short GRB. And there's been a lot of work, and I will not go into all of it right here, but I just want to say that the bottom line is that we know now that there has been a successful jet that has managed, successful meaning that it managed to break through the ejecta that is launched from the neutron-star merger after this initial merger takes place. So there was a jet, it was narrow, and it was pointing away from the line of sight. And just to mention briefly 2 ways that we know this. One is from the superluminal motion. So this is the motion of the flux centroid across the sky, which is moving in an apparent speed greater than the speed of light. So from this, you can calculate a combination of the viewing angle and the Lorentz factor of the jet. And we know this also from the decline of the afterglow. Here you see the afterglow from 170817. Notice the time scales. This peak here is on a time scale of 150 days. And then after this peak, you see this decline, which is very fast, which, as I told you before, suggests a successful jet. This is exactly like the jet break that we talked about earlier. And we saw that after this jet break, we have this very steep decline. So let's focus a bit more on this afterglow. You may have noticed that it looks very different to the types of afterglows that I showed you previously when we talked about cosmological GRBs. There, the flux was always decreasing. Maybe sometimes it was kind of flat, but it was never gradually increasing for very long periods of time. Like here, it's increasing for 150 days before it's finally starting to decrease. So why is this happening? Well, this is exactly connected to the fact that we're observing this jet off axis. So imagine that there is the core of the jet that is pointing away from the observer, and the line of sight is, as I drew here in this figure, towards some angle that is far from the core of the jet. So at early times, because you can only see material that is within 1 over gamma beaming cone to you, you're only seeing material that is not so energetic that happens to be close to the line of sight. before this material is decelerating, you see a very sharp rise in the flux. This is true also for cosmological GRBs, although usually we don't see this part. There's a very sharp rise in the flux before the material has reached the so-called deceleration point, before it accumulated enough of this external medium mass to slow it down effectively. Then, once this has happened, we start seeing this flux here, and it starts to rise. Oh, I don't know why this is going in a weird direction. It starts to rise gradually, as you can see here, as 1 over gamma is increasing, and we are getting closer and closer towards the core of the jet in our viewpoint. Eventually, we can see the full energy of the jet here at the peak, and beyond that point, since there is no more energy to gain by increasing 1 over gamma, the flux now starts to decline exactly like it would in a regular cosmological GRB that is seen after the jet break. So from here on, we've seen all the energy. It doesn't matter what our line of sight is relative to the jet, because we can now see the whole thing. So we understand this part reasonably well, but still, it may not surprise you, given the introduction. There's some big questions, especially regarding the prompt emission. And one of those big questions is whether the prompt emission that was extremely faint, I told you 10,000 times fainter than typical short GRB, is that faintness due to the fact that there is really almost no energy at these side lobes of the jet? So is it simply because of the fact that there's no available energy there? Or is it because whatever energy is available there is not emitting efficiently towards the observer in gamma rays? So maybe there is still quite a bit of energy, but it's somehow hidden from our view in the gamma rays. So these are the two main types of models that have been discussed, and we will want to see if there's a way to differentiate between them. Well, one way that one could imagine to differentiate between them is to calculate the characteristics of jets, the energy and the Lorentz factor in jets as a function of the angle. And indeed, this is something that people are working on and investing a lot of numerical and a lot of time and effort into this. And you see that the results are still not in agreement between different groups. So you get different types of structures depending on the exact assumptions that go into this calculation, and depending on the physics that are included in these simulations. So this is a very interesting line of pursuit, but we're still not there yet. And so maybe there is something that we can do right now with the observations that we have. So this is indeed what I would want to suggest. And what I would like to suggest is that we already have quite a few clues from prompt gamma ray bursts that have been seen just through the gamma ray emission from cosmological GRBs before 1708-17. And I will mention here 3 lines of argument along this direction, and then we will see where they lead us. So the first of these has to do with a correlation that people have noticed between the energy in the gamma ray part of the gamma ray burst and the luminosity seen in X-rays in the afterglow at some fixed time after the burst, say 1 hour after the burst. So you see here this correlation in the left-hand side. It has some scatter to it, but the scatter is not huge. Similarly, you can get, by the way, the same correlation if you do the most naive thing, which is not to try to get any sample that is complete in redshift and correct for observational biases, but just take all the Swift GRBs, look at their gamma ray fluence, and compare it to the X-ray flux at some fixed time. You get the same correlation with the same scatter. So let's see what this tells us. So we will assume for now that the energy that is seen in gamma rays is some constant efficiency relative to the available energy as a function of angle. Okay, we will see later if this assumption is justified, but let's assume this for now. And in that case, the energy that you see along some line of sight pretty much scales with the available energy. One caveat here is that you have to take into account Doppler beaming, so you have to really integrate over the flux coming from all the regions of the jet. So you can see on the left-hand side here, the solid lines are the actual emission that you will see, and the dashed lines are the energy profile of the jet. So you see that there is a difference, especially when you go to larger angles, you start being dominated by material that's further in, and so you get much more energy than you should get from just the available energy along the line of sight. Now, for the afterglow, the story is very different. For the afterglow, the luminosity that you see depends very critically on how close this material is to the deceleration point, to the point where it's accumulated enough mass to slow it down significantly. And that turns out to be very critically dependent on the Lorentz factor. It goes at the Lorentz factor to the 8th power. And what this means is that if you look at the ratio of these two things, and if you take any distribution in Lorentz factor that is not very, very close to flat, you will see that once you go beyond the core, so this is this ratio as a function of the angle, once you go beyond the core, here in the right-hand figure, you will start seeing these huge deviations by many orders of magnitude. And this is, of course, not what was observed and what I showed you in the previous slide. So one can take this and do this in a statistically more robust way, spare you the details, but the bottom line is kind of captured by this figure. So if you imagine that the energy goes as theta to the minus alpha beyond the core of the jet, and the Lorentz factor goes as theta to the minus beta beyond the core of the jet, you can basically rule out a large region of parameter space due to this type of consideration. Next, there is another line of argument which has to do with the luminosity function. So the luminosity function is basically, you take GRBs, you try to correct for observational biases and so on. And once you do that, you try to ask what is the distribution of the gamma ray luminosities in their central engine frames. And you get something that looks like these blue curves that you see here in the figure. And the point here is that imagine that you have a jet with some kind of luminosity along the core of the jet. For every copy of such a jet, there will be many more similar jets that are viewed at a large angle off axis to the jet, simply because the solid angle that is associated with larger viewing angles is much larger than the solid angle associated with smaller viewing angles. So that means that there is an unavoidable, very soft component, very soft tail to this luminosity function in models that have significant structure beyond the core, because you're often going to observe them far away from the core, and that will contribute to low luminosities. And you can see an example of this in these orange crosses. So this is for a particular model that is characterized by the parameters alpha and beta on the top of the figure. And you see that it clearly over-predicts the results based on the observational studies. So again, this can rule out a significant part of the parameter space. Putting those two things together, you end up with a pretty narrow region where the energy has to be pretty steeply declining beyond the core, and the Lorentz factor has to be very close to flat. Even that region, I will show you, is actually problematic. So let's take a Lorentz factor that is fully flat beyond the core, an energy profile that is quite steep, and only select for those bursts that are still detectable at, from their gamma rays at the angle that we observe them. Even when we do this, which restricts the viewing angle, we will still very often have bursts that have these afterglow light curves in X-ray and optical that you see here on top that are very shallow. They have these very shallow phases and maybe even shallow rises that last tens of days. And this is something that is never seen. In fact, you can see here at the bottom a plot of many, many long GRBs all together. And on these timescales that we're talking, the fastest they ever decline is t to the minus half, which is still, sorry, the shallowest they ever decline is t to the minus half, which is still not nearly as shallow as what we expect to see from any one of those events that should be actually extremely commonly seen, because again, the solid angle associated with such events is very large. So in fact, even this allowed region is actually problematic because it produces afterglows that are not like the ones that we observe. So we've essentially ruled out all of this parameter space. So what is the solution? So an alternative possibility is that the assumption that we made early on, that the gamma ray energy scales directly with the energy content, is simply incorrect, and that the efficiency of producing gamma rays is a strong function of angle. If you take as an extreme example that the efficiency drops as a theta function beyond the core of the jet, then you immediately reproduce consistency with all these different considerations. And more generally, what you need is you need to have the Lorentz factor of the material from any part of the material that is effectively radiating towards the observer always be very large, let's say 50 or larger, and you need the viewing angle, maximum viewing angle of any of those cosmological GRBs to be reasonably small, up to say 1.5 times the core angle of the jet. One way to do that is to say that the emission at large angles, similar to the one that was seen in 1708-17, was because of the fact that the efficiency was suppressed because of the fact that the efficiency is very low at these larger latitudes. And there is a physical way to do that, which is a shock breakout from a cocoon, but this may not be the only way. How can we actually test if this is what's going on? So one way to test this would be to start seeing more events which are seen in coincidence between gamma rays and gravitational waves. So we have one so far, but over time we will start seeing more of these events. And even just the rate at which we see those events will tell us quite a lot about the energy structure in the jets that are associated with these neutron star mergers. So between these different models, the difference in the rate of coincident events in gravitational waves and gamma rays could be a factor of 10. And furthermore, if we start seeing several events, we can start looking at the distributions of the luminosities, distribution of those observation angles, and those over time will again reveal the structure. And you can see here predictions for the two different models that I discussed earlier, and you see that they differ quite significantly. So we don't need many events before we can start differentiating between these possibilities. So before we kind of have this information that will only be available over years and maybe even more, maybe 10 years, then we still want to do something with what we have available now. And now I want to go back to cosmological GRBs, but this time look not at their prompt properties, but at their afterglow properties. And I mentioned earlier in the talk that there is some characteristic of GRB afterglows that is often observed, in about 40% of GRBs this is observed, which is this plateau phase. So this is a phase where the afterglow is flat or almost flat, maybe gradually declining or gradually increasing. And this can last between 100 seconds and 10 to the 5 seconds. There's a very wide range of values for the time scale of these plateaus. And there have been various explanations to try and explain this, but this does not come naturally from this Blandford-McKee model that I told you about before. So something has to be added on top of this basic model. And what I want to tell you about here is our explanation for these plateaus, which has to do simply with the viewing angle effect. So we are not adding any extra components to the jet. We're not injecting energy or anything like that. We're just saying that in some events, you're going to be viewing very slightly off axis. And if you remember, I just told you that we never observe bursts very far from the axis, but we can observe them from maybe a few tens of % of the jet core angle beyond the core. And that is enough to produce these shallow parts in the light curve that will have the right type of time scale and the right type of luminosity to reproduce the plateaus. So you can see some of the math here in the slide, and you see that the important thing here is that the dependence on the viewing angle is very sensitive. And if you go from a viewing angle that is 0.01 to 0.03, you can really change the timescale of the plateau by orders of magnitude. And you see an example here, depending on what is the external medium that is decelerating the jet. So this could be constant density or a density that declines as the radius to the -2. and you see the different light curves that we calculate for different viewing angles relative to the core. And you see that we can get these types of light curves that can be flat and can be flat for a very long time after the original burst. You can also see that there is this sort of bump-like structure in the light curve here. And I want to show you some real light curves so that you can compare what this looks like. And you can see that in many real light curves, and this is just a selection of a few, you actually see this structure, what we call plateaus in gamma ray bursts. They are not always plateaus. Very often you see these sort of shallow bumps in the light curve, which is exactly what we expect from this off-axis model. So another kind of nice feature of this model is that there are correlations which are known to exist between properties of the plateau and properties of the afterglow. For example, between the luminosity of the plateau and the energy of the afterglow, or between the ratio of those two things and the timescale of the plateau. And you see here in circles the data, and in color you see the results from our calculation. And you see that they match very nicely. And this can also be understood from very simple considerations, simply because the total energy in the plateau will roughly scale with the total energy of the gamma rays. In this model, both have to do with the amount of energy in the core of the jet that is initially hidden from view. And this is not the case in, for example, the model that invokes energy injection to create the plateaus, because in that model, it's not clear why this energy that we see in the gamma rays, which is a small fraction of the total energy that will eventually be in the jet, is related to this energy that is later injected, and why those two should correlate. This type of model also explains the fraction of bursts that have and don't have plateaus, simply from solid angle considerations. It also explains why we don't see a break in the spectrum between the time of the plateau and after the plateau. And it can also reproduce the fact that while we see a plateau in X-rays, often we see something that has no plateau, maybe rising or declining in optical. If this interpretation is correct, one nice feature that we are now exploring, and this is still in preparation but should be out soon, is that the same interpretation will also suggest that we can explain X-ray flares from de-boosted prompt emission. So imagine now that you're viewing slightly off axis, there is something that would have produced a prompt emission spike if you were to see it along the core of the jet, but now you're off axis, so it's relativistically de-boosted, so it will appear at later times, at lower frequencies, and it may look like this flare that is seen in X-rays in GRB light curves. So this is quite encouraging. We have initial results which seem to look promising for this interpretation. We're still exploring the details. But if this is true, it really means that maybe we can answer two of these big questions in GRB afterglows with sort of a unified explanation. This also will constrain each one of those explanations further, because really we are, from one set of assumptions, we are now predicting many different things. And if this pans out, then it will give us significant constraints on the structure, at least around the core, not very far away from the core, from this sample of cosmological GRBs. So this is still work in progress. Finally, if I have some more time, how am I doing for time?
Yes, you have plenty of time. You have roughly 20 minutes.
Good. So finally, I want to talk about what can we do in the future when we have more events detected in gravitational waves and also with electromagnetic counterparts. And I talked before about the population that will be detected in prompt emission from those gravitational wave triggered events. But actually, much more common would be to detect a counterpart in the afterglow. So the afterglow, especially in the radio, is bright enough that it can be seen for a large fraction of these GRBs that will be detected by LIGO. And so over time, we will start seeing more and more of these afterglows from GRBs that are off-axis. And so it's good in that sense to start and try and develop tools to understand these afterglows better and more intuitively. So what you can see here is the map of the flux on the sky coming from such an afterglow, where the jet is on the white X here to the left of each one of those plots. The observer is at the center of each one of those plots. And these different circles basically show you where most of the flux is coming from. And you see it as a function of time. So time here goes from left to right, and then the same in the bottom panels. And you can see that initially, your viewing angle, the material that is shining towards you is coming very close to the viewing angle, so very close to the line of sight. Over time, you see that this area that dominates the flux goes closer and closer to the core of the jet until eventually it's completely centered on the core of the jet. And there is a lot of information in this figure, and you see there's this whole distortion of the shape of this flux map as it moves from being centered on the observer to being centered on the core of the jet. But one very simple characteristic of this is what I call here theta min. This is the smallest latitude, the latitude closest to the core of the jet, from which, taking into account Doppler beaming, we can still view the emission at our line of sight. So this is this equation that you see here. Basically, it says that 1 over gamma from that angle still reaches us. And this angle changes as a function of time. You see here how it changes as a function of time. And you can also see here, sort of as a side result, that we can calculate this analytically. And this is what you see in the dashed line. And the results are pretty much exactly the same as what you would get from calculating this numerically from integrating over this whole flux map that I just showed you. So we can get a very good handle on this angle from analytical considerations. And the asymptotic behavior is also simple to understand even from back of the envelope type calculation. It basically depends only on the energy structure of the jet. This is T to the minus 3 over 8. So with this in hand, let's see what this tells us about the shapes of afterglow light curves that will be detected from off-axis events. So I will do this with the aid of this kind of simple figure here. So what you see here is the profile of Lorentz factor times theta as a function of theta. And I'm plotting it from the core and outwards. So it's always declining, it's some power. At t equals 0, you have this solid line that extends all the way from top left to bottom right. And now, as time goes by, so let's imagine that we are at some time t1. At time t1, there is an angle that is currently being decelerated. Everything below that angle is already decelerated. Everything above that angle still is the same as the initial profile. The reason is that typically, because the inside of the jet is moving much faster, and the Lorentz factor of the jet is the most important property for determining when things start to slow down, typically the jet will start to slow down from the inside out. The opposite is also possible, but it's not so likely. And so what this means is that we have this theta deck as a function of time, which will be going over time towards the right. We can also define another interesting angle here, which is the angle from which beaming is important. So this is theta beam. And at time t1, you see that it intersects with the Lorentz factor profile at this point. So you see that as long as we're looking at angles that are below theta star, or at times that correspond to those angles, the order between theta beam and theta deck is always going to remain the same as I drew it. But beyond that point, at T2, you will see that this order is going to be reversed. And now, already from the start, there is material that is further inside from the viewing angle from which beaming is not important, and we don't need to wait for that to happen at some late time. So what this means is the following. Let's imagine two different situations. One is the situation where the initial viewing angle is less than theta star. If the initial viewing angle is less than theta star, then the initial gamma theta along the line of sight is greater than 1. What this means is that at early times, I have this picture similar to the cosmological GRBs that I described earlier in the talk, where relativistic beaming is important, and I don't know about the final extent of the jet, so I will see something that is increasing before the deceleration time, and then starts to decrease. Eventually, as this inside of the jet is decelerated more and more, eventually this theta beam becomes close enough to my line of sight that I start seeing emission also from angles closer and closer to the core of the jet. So I start seeing this gradual rise in the afterglow, like we saw for 170817, and then the eventual decline once I've seen the full energy. In the opposite situation, if the viewing angle is greater than theta star, then from the very first moment, I can see emission from theta star, because from theta star, by definition, everything is visible to all viewing angles. So from the very first moment, I am not trapped in this narrow beaming cone around the line of sight, but I'm already in this gradual increasing phase, and then have the decline later. So this is also summarized here in this plot where you see theta as a function of time, and you see that there are two times of behaviors in terms of the order of theta beam and theta deck, depending on if the viewing angle is greater than theta star or smaller. And the result is basically that we can get either a double-peaked light curve or a single-peaked light curve. So if theta observed is smaller than theta star, we will get this double-peaked light curve. And if it's vice versa, we will get a single-peaked light curve. The dashed lines here come from a fully analytic calculation. The solid lines come from numerical integration over the jet, the flux coming from the jet. And you see that the agreement is pretty good between the two. And the advantage, of course, of this analytical calculation is that, well, first, we can understand things a bit more intuitively. Secondly, it's very easy to use, very easy to implement. Basically, it takes no time if you put it into some computer to try to get some parameters for the jet from given observations. And if we focus on the shape of the afterglow, rather than the normalization of the times and fluxes, then we can get the slopes, the time ratios of the two peaks if we have two peaks, and the flux ratio of the two peaks if we have those two peaks. We can get all of those things completely independently from the parameters that are usually mostly degenerate in fitting GRB afterglows, and which are the most poorly constrained, which are the ones that are listed here towards the top: the density, the energy, the fraction of energy going towards relativistic electrons, and the fraction of energy going towards magnetic fields. Instead, all this depends on, when we focus on those properties, is the viewing angle, the structure of the Lorentz factor and the energy, and this compactness parameter of the core. And you can see some example equations at the bottom here, and you see that they're really quite simple to infer those parameters from the observed properties. So just to kind of demonstrate how this can be useful, so if we look at the 170817 as a test case, in that scenario, in that event, we only saw one peak. We didn't see the second peak. This could be because the second peak was not there, or it could be that it was very faint and or very early on that we just missed it. But this gives us some constraint on the parameter space, which you can see here that I said the time of the peak has to be at least 7 times larger than the time of the deceleration of the smallest viewing angle observable to us early on. And the analytical constraint that we get from this is this colored region that we see on the left-hand plot. And you can do now a numerical fitting, and you find that this region is in very good agreement with this numerical fitting for those parameters that I have here, which are the structure of the Lorentz factor profile and the value of the Lorentz factor at the core of the jet. So we get good agreement, we get some interesting constraints on those parameters, and these are things that may be hidden if you do the thing that people usually do when they try to fit GRB afterglows, which is they have some numerical fitting procedure which has lots of free parameters, and it tries to search for through this very big parameter space for solutions that can reproduce the light ray. This is, on the one hand, something that is very accessible and people are doing very commonly and have been doing so for a very long time. But we should bear in mind that there are many, many parameters to search through. And so this is can be somewhat wasteful, especially when you take into account structures of jets. So this adds many free parameters. And secondly, there are degeneracies. And these degeneracies mean that there will typically be many solutions that are acceptable, and we won't necessarily know which one to choose. This kind of methodology that I'm suggesting here helps us to know which parameter space, which area in the parameter space to focus on. So kind of a side result is also that we can constrain very strongly the Lorentz factor along the line of sight from this argument. And the results agree with the different constraints that we have from independent arguments. So I will conclude now. So in conclusion, I argued that in most gamma ray bursts that we see from cosmological distances, and especially the long ones where we have good data, then if we have this structure beyond the core, then efficient gamma ray production still must only be taking place very close to the core of the jet. It's restricted to material that is moving very fast and at angles that are not too great beyond the core of the jet. However, if you are looking at those angles which are slightly beyond the core of the jet, that can introduce some interesting features in the afterglow light curves, such as plateaus and maybe also X-ray flares. This is simply from the D-beamed emission from the core that is joining the flux at a later time. In short GRBs, if we want to understand better the structure and the efficiency of gamma ray production, we will be able to do so from joint detections of prompt gamma rays with gravitational waves, looking at the rates and looking at the distribution of the luminosities and viewing angles. And looking at the afterglows of the same events, we will be able to constrain the parameters of the jet quite efficiently if we focus on the shape of the afterglow rather than on the normalizations. And we have this prediction for these two types of afterglows that could be observed. It would be very exciting to see this kind of double-peaked one, but we have to wait and see. So finally, I just want to advertise that we have postdoc positions available at the Open University. There's an ad on AAS, so I encourage you to take a look if you're interested, and I will conclude here, and thank you for the time.
Thank you very much, Paz, for the excellent talk and for being on time. Yes, I think that people will have questions because you talked about many new and interesting things. So I have questions, but I'm going to wait for others first. So please either raise your hand or unmute yourself and ask your questions. Yes, I see one hand by Apostolos Mastichiadis.
So hi, Paz. Thank you for your talk. Probably we met when I was in Jerusalem about 10 years ago.
Yes,
you were a student.
I remember.
Yeah, I was visiting in Sweden. Very nice talk. I missed some parts because I had some problems. But now, about your X-ray plateaus, what you do about the flares that appear at much later times? Because we see some X-ray flares that are 10,000 seconds later. Could you explain all these flares with your model?
Yes, so I agree that those would be more difficult to explain with our model. The ones that we most naturally explain are the ones that are not very late relative to the prompt emission, because once you become, once the time of the flare is going later and later relative to the point emission, then the deboosting that you need from the gamma rays is more and more significant, and yet you wanted to still shine in the X-rays, so that limits how much deboosting you can have. You want to go from gamma rays to X-rays, and so it's quite difficult to reproduce those very late flares. So this is one of the things that we are trying to understand. It's possible that there's more than one type of flare going on in gamma ray bursts. There is some evidence for that. There's a study by Marguti et al. Looking at the luminosity of flares as a function of the time at which they appear, and there seems to be a break in this distribution at about 1,000 seconds. So there is a correlation going on up to 1,000 seconds, and then a different correlation beyond that. And so it could be that there are two different mechanisms in play here, but we still have to get to the bottom of this.
Okay. And thank you very much. Another question is, if I understood correctly, you took a gamma factor that depends on theta, d, e, d omega that depends on, again, what about the radiative process? You assume that throughout the afterglow, you don't have any cooling of electrons. It's a constant injection, and you simply care about what energy you put, but not how. I mean, if you have synchrotron radiation, that electrons cool,
yeah.
It's you change the magnetic field, you have all these things.
Yeah.
Is it
so this is
I
folded into the calculation. I kind of skipped it in my explanation because I wanted to keep things simple. But when we produce these light curves, we take into account where you are in relative to the cooling frequency, the synchrotron cooling frequency, and the synchrotron injection frequency. Now, this statement that I made that we only care about the shape of the afterglow, and when we care about the shape of the afterglow, we are independent of these parameters of the density epsilon E and epsilon B. This is only true as long as we're within one spectral portion of the afterglow. So let's say that we're always below the cooling frequency. Then as long as that's the case, this statement is true. If at some point during the observation we switch from being above cooling to being below cooling, then we will start introducing dependencies on these parameters. And that is possible, but luckily, it's actually maybe not expected to be very common. So for example, in 17017, which has observations spanning a very wide range of timescales, all the way from 10 days to now 1,000 days and more, the flux that we see in both X-rays and radio, so huge level in frequency, are always below the cooling frequency and above the injection frequency, always in the same spectral portion of the synchrotron. Mm-hmm. So that is a lucky coincidence in a way, but yeah, it's certainly true that if that was not the case, this will complicate our lives and mean that we will have to take account also of all of these other parameters.
Okay. Because some years ago with Maria and Zvi, we were trying to explain these plateaus simply by shifting the frequencies of because of the cooling and of the electrons that you had. But okay, that was, I'm not sure how this stands, but it was another idea that I was working with Zvi. Mm-hmm. Okay, but this is extremely interesting. All these geometrical factors that you propose and the predictions. So thank you.
Okay, we have more questions. I see one raised hand by Professor Vlachakis. He also wrote something in chat. So
yeah, let me ask it. Mm-hmm. Thank you, Paz, for the nice talk. So my question is, suppose that the emission comes from a cone, an empty cone, a conical shell, compared to yours hypothesis that is coming from a region near the axis. What can you comment on the differences? Is a way to rule out this scenario?
Yeah,
I'd like to hear
one of the big
on
differences. So actually, the figure that I have here on this slide is a relevant one, because one of the big differences is going to be in the smoothness of this transition from the gradually increasing phase to the decreasing phase. This smoothness depends on a combination of the viewing angle and the size of the core of the jet. You can imagine it as you start entering this peak when theta observed minus theta 0 is exactly 1 over gamma, and you exit it when you go to the other side of the jet. And so if there is a hollow cone in between, the shape in between here and this transition will be affected in this way. So these are things that we will have to have, but it's, as you can imagine, it's quite difficult to constrain those things because all of this will be happening on a relatively short time scale, and you have to have very, very good data to be able to distinguish small features. You can see the quality of the data that we have for 170817 here, and you can imagine that it's easy to kind of put some wiggles in there and we wouldn't notice, right? So we are not there yet, but in principle, this would be a way to hold that.
Okay, so there are 2 questions by Professor Tsinganos written in chat. Would you like to ask them yourself, perhaps?
Yes, because actually there are 2 questions and I can put them together. First, I would like to thank the speaker for sharing with us his work and showing all these interesting things that happen with GRBs. I am coming from a slightly different community, namely the MHD community. You know, these objects, besides the energetics, they have the dynamics. And actually, they are interrelated because one assumes for the energetics some kind of configuration for the dynamics of the outflow. So a usual question that we have when we work on MHD is the structure of the outflow. Until today, we assume that there are 2 components in the jet: a spine, a relativistic spine, surrounded by a slower, well, we call it sometimes disk wind or something slower. Okay. Is this something that you also assume, because you focus on the energetics clearly, okay, and I'm not really an expert on that, but how the assumption on the structure of the jet affects all these results that you have shown to us. That's my first question. And the second related question has to do, you mentioned the analytics, yeah? I mean, you mean the analytical treatment. Again, what kind of assumptions do you make as far as the geometry of the flow and the radiation in this analytics, the analytical work that you mentioned? These are just, I mean, maybe there are some naive questions, but I'm not really an expert in the energetics part of the jet. But from the MHD part, these are something that worries us, like the ones Nectarios Vlachakis has asked before, on the relativistic jets in general and GRBs in particular.
Yeah, thanks. So for this study that I showed with the afterglows, we assume that the energy is constant, roughly constant, up to the core, and beyond that decreases at some power law. We let this parameter of the power law be free, and the same for the Lorentz factor, constant up to the same angle, and then declining as some power law, and again that power law can be free. Now, we also explored other models. For example, we looked at the model where the structure of both the energy and the Lorentz factor can be described as a Gaussian function. And the good thing is that the qualitative results of having these 2 types of light curves and this characteristic theta star that differentiates them, these are largely independent of the family of structures that is considered. If you take these Gaussian structures, power law structures, you would still get that. And one can also start looking into models that are more involved. And in fact, this is something that we're planning to do, taking models that come directly from MHD simulations of jets and doing this analysis with such models. This is exactly the next step of what we're planning to do. One thing that we just started kind of looking into is can we see any differences between hydrodynamical jets coming from simulations to MHD jets coming from simulations using these types of observations and this type of analysis. So
yeah, but in a hydrodynamic, if you don't have a magnetic field, you don't have radiation. I mean, you need to put the magnetic field at some point.
The radiation is added on top, so that is coming from this external shock in this in the afterglow. So in the afterglow, the radiation is, as opposed to the prompt emission, in the afterglow, the radiation is well understood. Basically, what you care about is really mainly the energy and the Lorentz factor in a given angle. As those start colliding with the external medium, they shock the external medium, and it's the emission from that shocked external medium that you see. You don't actually see, most of the time, you don't actually see emission from the jet itself at the afterglow. You see emission from this shocked external medium that is shocked by the jet. And, and that process is much better understood than for the prompt emission. And so for that, we can really be more secure that we care about the energy content and the Lorentz factor in the jets. And then we can start kind of comparing the results that are coming from different jet simulations with different assumptions.
Okay, thank you.
Has anyone else any question that would like to ask? If so, you can raise your hand. Yes, there is one by Antonios Nathanael.
Hello, thank you for the nice talk. So the question is there any physical reason why the gamma ray efficiency goes down after the core?
So that depends on what the emission model is. There are at least a couple of models where this is expected. So for example, imagine that we have internal shocks as the model for powering the prompt emission. This is kind of a model that has been around for many years, kind of in fashion, out of fashion, in fashion again, but without kind of trying to assess its validity. Let's just take it as a demonstrative example. So in this model, the idea is that you have different parts of the jet with different Lorentz factor. At some point they collide. This collision releases a lot of energy that is then giving us the prompt emission. Now, the radius of the collision relative to the radius of the photosphere depends very critically on the Lorentz factor. The ratio between the two goes as the Lorentz factor to the 5th power. This means that if you have these collisions take place below the photosphere, then all of this energy that was dissipated is not available to radiate to the observer because this region is optically thick. So it will still suffer adiabatic losses before it's escaping towards the observer. So the efficiency will be strongly declined in this case. Whereas if this takes place above the photosphere, basically all of it can be radiated. So you can have this kind of mechanism which naturally produces a sort of cutoff in the efficiency or a very strong decline in the efficiency, which will happen once gamma drops beyond a certain value, which is expected beyond a certain angle. So this is one way in which this can happen. This is just an example. There are different models that also will predict qualitatively similar things.
Okay. I don't see any other hands. My question was also related to Antoni's question. But I don't think that I understand why this would change the efficiency as a function of angle.
Okay, so let me...
And not as a function of...
Because Lorentz factor is a function of angle. So if this is very strongly dependent on Lorentz factor, and Lorentz factor is declining as a function of angle, then this will strongly depend on the angle. So for example, if along the core, the Lorentz factor is 200, and this is sufficient for the internal shock radius to be above the photospheric radius, then you get high efficiency. But if at an angle of 20 degrees beyond the core, the Lorentz factor is 20, then the internal shocks occur below the photosphere, and then you have this very inefficient.
Okay, so essentially you're changing just the location of the dissipation by considering the different gammas as a function of theta.
The dissipation and relative to the photosphere, because the photosphere itself also changes as you go
yes.
to lower Lorentz.
Okay. And a naive question, or maybe you said, but I missed it. I was wondering whether or not these double-peaked light curves of the afterglows have been observed, and if not, why this is the case. Because if I saw, I saw that the peaks happen relatively at late times, so I would have expected that it could be detectable by XRT or some radio afterglows for long GRBs.
Yeah.
So
good. So far, we only have 170817, which is the only afterglow which we observed clearly off axis. There's now one paper from people here in Caltech, and I'm co-author of that paper, where we may have seen an orphan afterglow, in which case the afterglow could be off axis, but this is, the observations are very restricted, and it's, we have maybe one or two, a bit more than one. We have a few data points, and we can't really see any temporal behavior at all. Definitely not early peaks like that. But generally speaking, 17817 is the only afterglow that was seen clearly off axis. Usually, we detect afterglows only after we've seen prompt from that burst, and we know to look at that location and search for an afterglow there. And that's a big limitation. That means that because we observe prompt on axis, we always observe afterglow on axis, and then we see things always declining in time. But all of these nice structures only appear when you're looking far away from the jet, but then you have to somehow still be able to trigger those events in the first place, and this is where gravitational waves will really change how we view this whole landscape.
But,
okay, thank you.
But excuse me, the event with the gravitational waves, if we leave out the gravitational waves, again, it would be triggered.
This event was actually very marginally detected by Fermi. So even if it would have been triggered, it definitely wouldn't have been followed up on with all of these X-ray and optical telescopes to the degree that it has. And it took 10 days before the first X-ray detection. So let me go back to this plot over here. These are all upper limits early on. In a normal GRB, if we have such upper limits, and by the way, they're never as good as this. This was really a huge effort by the community. Then we simply leave it. We never go back because there's no telescope time to devote to it. But here, they continued taking more and more observations, and finally, 10 days later, was the first actual detection of an afterglow. So it's that's a big part of why we see this huge difference between 17817 and the usual story.
So you are saying that maybe we had such detections in the past, but we never follow up. I mean,
it's possible.
And
that's right. That's one of the implications of the study that we did also with Maria and the collaborators, is that it's possible that some of the bursts that have already been detected by SWIFT are actually local GRBs off axis, which are sort of mixed into the regular population of GRBs, and we were unaware of them. They were hiding as if they were at much greater distances and along their core. And we don't expect that fraction to be large. We expect that at most it's coming from our rates, at most this is a few %, but there could be some like that.
Okay, I think that I don't see any other questions, and we are already 15 past 7. So 7:15. So I think that we can close this meeting today. Thank you very much, Paz, for the very interesting talk. It was nice seeing you and hearing to your latest research, listening to your latest research results. And thank you all for attending, and we're going to meet next week at 6 p.m. again. Thank you.
Thank you very much.
Bye. Thank you.
Thank you.
Thank you and goodbye.